Hello and welcome again to CHeM in 3. Today we continue to work with the topic of chemical kinetics for IB Chemistry HL, returning again to review the Arrhenius equation and how two other equations that are relevant to IB Chemistry are derived from this Arrhenius equation. It's important to note though that this Arrhenius equation is given in the IB Chemistry data booklet, and so too is this equation here, which is derived from the original Arrhenius equation. And then we'll go on to look at how a third equation, which is also provided in the data booklet, how that equation is derived. But it's important to note that IB Chemistry students at HL studying this topic 16 need not understand the mathematics involved in moving from the equation, the Arrhenius equation, to this form of the equation, which is the same as the equation of a line y is equal to mx plus c. And you need not understand how this then gives rise to this. But of course it is useful for you to understand the steps. Let's take a closer look. And here we take the natural log of either side of this equation. And by doing that, we get this expression. Then this expression can be rearranged, taking out this t here and making it 1 over t. And what that does is it brings the Arrhenius equation into a form that can be easily related to the equation of a line y is equal to mx plus c, where m of course is the gradient. And you can plot everything here with ln k, the natural log of k, going on that axis, 1 over t here, and the intercept on the y-axis being the natural log of a. And now we consider how we can combine two equations. Let's look at this question here. And these are the steps to go about solving the question. We have K1 and T1 brought into Kelvin by adding 273 to 27, K2 and T2 brought into Kelvin. Then we will have two equations, equation 1 and equation 2. Equation 1 with K1 and T1, equation 2 with K2 and T2. And then we say equation 1 minus equation 2. And that gives us this. Ln K1, the natural log of K1, minus ln K2, the natural log of K2, equals activation energy with a negative sign in front of it, divided by RT1, plus activation energy, note there's no negative sign, plus RT2. And this happens because in subtracting the equations, the two ln A's would cancel. Then negative EART1 minus EART2 translates into this positive sign, with the negative being retained here. Next, we consider what ln K1 minus ln K2 translates into, and using this rule from logs, where the log of x minus the log of y equals the log of x divided by y, then we arrive at this equation. The natural log of K1 divided by K2 being equal to activation energy divided by R multiplied by 1 over T2 minus 1 over T1. Notice the rearrangement that occurred from here, with this coming to the front, so this having a positive sign, T2 minus T1 being put into brackets, and EA divided by R being brought out of the brackets because it's common to both terms. And this equation, even if you're struggling to understand how it's derived, need not bother you, because it's all provided in the data booklet for IB Chemistry, this equation. So to solve this question, it's just a matter of figuring out what goes into K1, what goes into K2, and especially remembering to convert temperature into Kelvin before plugging into this equation. And then you go ahead and you plug it in like this. It's really important to get familiar with your calculator and to know how to get the natural log and how to carry out all of these calculations. And the final answer brought into kilojoules is 27
kilojoules per mole, with the answer being kept to two significant figures.